Ecco, dicevo intanto un caro saluto a tutti quanti per questa iniziativa portata avanti e promossa dalla cattedra Piero Pasolini dell'Istituto Universitario Sofia, cattedra che oggi tratta un tema centrale nell'evoluzione del pensiero di interazione tra uomo e tecnologie, appunto il tema del transumanesimo, termine coniato già nel 49 da Pierre de Chardin, ma che molti sostengono ha radici anche più remote, umaniste e illuministe, e che ha assunto ormai diverse definizioni e connotazioni. Prima di iniziare però vorrei dare veramente un gradito saluto ai nostri ospiti, relatori, che hanno aderito all'iniziativa e per il contributo sicuramente significativo che forniranno al tema. E ringrazio poi tutti voi che siete intervenuti sia in sala, so che tanti si sono collegati anche via web, ho diciamo un elenco di vari luoghi che dico velocemente: Australia, Kenya, Bielorussia, Israele, Brasile, Austria, Stati Uniti, Portogallo, Scozia, la stessa Italia ovviamente, e sicuramente da qualche altro luogo che man mano aggiorneremo. Quindi un caro benvenuto veramente a tutti. Solo diciamo una nota tecnica: le traduzioni sono in italiano e in inglese, quindi ciascuno di voi poi selezionerà anche in web la lingua che preferisce. Il pomeriggio è molto intenso, quindi io proprio per procedere velocemente, visto che abbiamo perso qualche minuto, anche lascerei per i saluti iniziali il professore Paul O'Hara, che è il direttore del centro della cattedra Piero Pasolini. Prego.
Well, thank you everyone for coming and participating. As mentioned, I'm the director of the Cattedra Piero Pasolini for Razionalità Scientifica and Ontologia, and rational scientific reasoning, if you like, and ontology. 2 words: Piero Pasolini is the Cattedra Piero Pasolini sponsors this annual event, and the name Piero Pasolini refers to a focolarino, a member of the Focolare movement, which is the founder of this university, who in 1942 wrote a thesis in physics at the University of Bologna, and it got was considered the best thesis in Italy of the time in physics. In fact, he won the Marconi Medal for the best physics, for the best thesis. He met the Focolare movement later in 1949 and helped Karl Luebig, the founder of the Focolare, to help diffuse the ideal of unity, which is at the core of the Focolare movement. But being a physicist, he remained with his faculties and his use of reason, although he didn't do, let's say, physics on a professional level. After that, he constantly was writing and updating, especially on a journalistic level and a popular level, communicating what has been discovered in physics. So the Cattedra is called after him. Having said that, don't want to waste more time. We have an honor of Manuela Veloso here is our guest speaker of the day. She's very, very renowned internationally. Did a laurea first in Portugal and then later went to the United States, where she's had a splendid career. I would just note that Forbes magazine has recognized her as amongst the 10 most important and influential women in the world in the area of engineering. And this year she was elected to the National Academy of Engineering, which is an exceedingly prestigious position in the United States and the world. And having said that, maybe we can just turn straight over to Manuela and have her talk. I know she has to go. She has another appointment by 3 o'clock our time. So Manuela.
Perfect. Thank you for having me, and thank you for the kind introduction. I'm just going to jump into a few thoughts. It's a little bit ambitious what I'm going to try to tell everybody, but let me see if we can cover at least a few of the topics. So the first thing I was going to do is to tell you a little bit about AI. AI stands for artificial intelligence, and basically it started in the beginning, in the mid-30s, with this man, Alan Turing. And Alan Turing somehow introduced the concept that computers could do more than just computation, number computation. And so basically he hypothesized that computers, machines, could actually think. And he introduced a very important, what we call Turing test, in which basically he said, if a computer, hidden computer, and a human would be interacting with another human that would not know whether it's a computer or human, can that evaluator decide or know which one is a person and which one is a computer? As of today, we still run this Turing test. It's very hard to, of course, have a computer be like a human in terms of like this interaction, but it's a very good challenge for the field of AI to try to achieve this Turing test. If you have not seen that movie called Imitation Game, I think it's a good thing to watch just to see how much Alan Turing believed or introduced the concept of really machines that do more than multiplications and divisions and all sorts of like numerical computation. So this was like the real beginning. I mean, for me, it was one of the beginnings. But then there is this famous time in 1956, so a few years later, about 20 years later, that there is this group of 10 people led by McCarthy Minsky, who for the first time used this term artificial intelligence, that wrote a proposal, and they wrote a proposal for the American NSF, National Science Foundation, or other funding institution to give money for this following purpose: to have 10 people for 2 months have this kind of like summer conference in which basically they say that they were able to do this study to proceed on the basis of the conjecture that they were believing that every aspect of learning or any other feature of intelligence, and this is the important thing, could be so precisely described that the machine could simulate it. So they thought, I mean, they thought that in some sense they were going to be there 2 months, 10 people, in fact, 10 men in this particular case, and that they were able to solve the field of AI. But in some sense, it's a young science because it just started, but it was very ambitious. And this proposal was actually funded, which meant that someone believed that this was going to be possible, and we are not there yet for sure. So I just want to highlight that in addition to having told for you to watch The Imitation Game, maybe you also want to Google these two people, Herb Simon and Alan Newell, who I knew very well, both of them. And Herb Simon, in fact, my chair at Carnegie Mellon is named after Herb Simon. And he's the Nobel Prize in economics in '78. And Alan Newell and Herb Simon started, in some sense, AI at Carnegie Mellon, where I've studied since I was in 1986. So these are important things to know. And now I'm just going to go on and tell you like just a little bit about then this AI field is driven by many questions. Some people are very interested in understanding what is the nature of human intelligence. Other people want to understand from a physiological point of view, how does the brain work? Other people are more engineering. I'm more on the engineering side. How do people solve problems effectively, and how could machines do the same? How do humans and machines learn, the problem of machine learning? How do we create intelligent creatures, robots? And I'll talk about this. How do humans and AI interact, and how can AI have values, ethics, explainability, fairness? How can it have correct values? And how can AI contribute for the social good? How can AI help reduce poverty, increase fairness, make people more concerned about peace? So all these social good, how can AI help? So the community who does research in AI ends up guiding their quest for intelligence in machines for different types of questions. So it's a very broad field, given that, in fact, artificial intelligence is a very broad topic. So this is like generalities that we can talk about, but there are many definitions of AI, but I like one in particular that I think that you need to understand, and I'll at the end, if I have time, I'll finish also with some thoughts that AI is the science and engineering, because we need to use artificial devices, computer hardware and software, sensors, actuators, and so forth, to exhibit human capabilities. And in particular, the ability to have perception, understanding of data, a visual, language, speech, all sorts of like data, cognition, which is the ability to reason and learn, action, execution, and interaction, and to solve problems addressed by humans. So this has been a definition that I believe captures many of the things that we try to have computers do. And I'll be happy to then answer questions at the end. One example that I'm going to just highlight is that in the 90s, late 80s and 90s, like 30 years after the Dartmouth conference, people were very focused on computer chess, which meant that a machine would play the actual game against a human. And there is these, well, at Carnegie Mellon, there were many, at CMU, there were many efforts on this computer chess when I joined in 1986. I was not involved with those, but I knew all these people. And then in 1997, there is this kind of landmark in which Garry Kasparov, who was one of the best player in the world of chess, was defeated by a computer program, basically Deep Blue, an AI system that was able to win games of chess against Kasparov. This is a landmark. There are many landmarks now and later, but I think that that gives you an idea of what people thought intelligence was, playing chess and basically beating Kasparov. But I met Kasparov in, well, actually, I only met him personally in 2012. We were both speakers at this Turing 100th birthday celebration in Manchester. And the interesting thing was that Kasparov told me something that I will never forget, because he was saying that in the early days, when he started playing chess, he was a kid, if someone played chess poorly, really bad, he would tell, or everybody would tell, oh, you play like a computer, like saying you really are not good. And then now, if someone plays really well, now people say, oh, you play like a computer. So that shows you the evolution in some sense. And this conversation with Garry shows the evolution of like how AI and computers have been improving over these years on a particular task, this particular chess task, but it has been like a science that has developed itself. And I still remember Garry Kasparov, I mean, telling that indeed, in order to learn to play chess now, well, the best thing is to play against a computer and try to learn from computers playing chess, which is remarkable, this kind of like accomplishment of a computer being able to perform these supposedly hard task. Okay, so I'm going now to spend, so I told you a little bit about AI at the beginning, then I told just this example of computer chess, but I'm just going to spend now a little bit of time, and then I'll talk about robots at the end, just mentioning about machine learning, because this kind of like a transition from becoming better, worse to better, has to do with machine learning. And so we'll now stop a little bit and we'll refocus. I'll come back to the robots, but I want to just tell you about machine learning and demystify what machine learning is all about. Or at least if you all know, it's fine, but just to set up like what is this machine learning. And you have heard about deep learning probably, so we'll talk about that. So let me tell you what is this. So usually AI or computers are given data. Data are basically examples of some function. So for example, let's look at this very, very simple example. We probably all know what this means, but it's an axis and a function f of x. And suppose that we are given these kind of like examples, which are these little crosses of some function, which we don't know what the function is. So AI is machine learning many times is about trying to learn from the data what the function is. So when you see this, there is people like what computers do, what AI does, machine learning does, is to try to fit a function to the data. So for example, this is a line that fits more or less 4 good data points, but does not fit the other 2. But, you know, that's the computer can think, okay, maybe this is the function. And there is a very important concept here. Maybe these 2 that don't fit this function very well are noise, are data that was given to us from the function, but that's like data that's actually not really correct. It's just some kind of like incorrect data. So this is an example. But another example would be to match not a line now, but to match a little bit more of a complicated function. This is a function with 2 parameters or 3 parameters. So it's a quadratic function. So it's not a line. The line is the simplest function you can think of to match data. But this is another one. Well, it matches 1 more point, which is good, 1 more data sample. So it's a better kind of model for the data, but it misses still 1. But you could do this one, which this function is more complicated. It's much more complicated. It's now basically 1, 2, 3, polynomial of degree 3. So it's more difficult because now you have to adjust more parameters. You have to actually find that curve. But you could also do one thing that, and here is what I want you to notice. You could have done this particular function. This function also fits all the points. They are all on this yellow curve, except that there is this assumption that what we don't know, that's in between all these points, which we have not seen from the data, that is very chaotic. So this is not a good function in the sense that it makes a lot of assumptions of what we don't know. While this function assumes that what we don't know is very similar to what we know. But what you need to understand is that this type of like, how do you say, function matching to data is what computers in machine learning do. So a computer is trying to go, to search, to go over all possible functions, and from very simple functions to very complex functions, and try to see if they find a function that fits the data. I want to say one more thing about this yellow function, which is very important for us to understand. So the computers, when they try to, how do you say, find a model, kind of like a function to this data, the goal of this function is to please understand one thing, is to use this now blue model, for example, to, if I want to know something that I did not know from the data that the model tells you. So for example, if I want to pick an X value that does not match any of these crosses, so I've never seen this particular point, then I just go from that point to the blue curve and I have the value of the function. So it's very beautiful, the concept of trying to generalize from the function. It's like, now let's look at not functions, but some data. For example, let's think about this. If you have examples of people who live in a particular area, going to a particular restaurant, or this other area, they go to this restaurant, and you have all this data where people go to restaurants or where people go to buy their products. So you have all these data. And then you want to find out where people who you don't have the data for will go to buy their products or will go to a restaurant. So the goal is to get examples and then figure out the things we don't know, what will happen given what we know. So I hope this is a little bit, I'm trying to make things that are a little bit complicated from a mathematical point of view to make them simple. So, but anyway, so this is how do you say, the ABC of machine learning. So if you are listening to this, at least at the end, if someone tells, oh, I have a learning algorithm and so forth, you understand what's going on. It's such some data points, and basically you try to find some way of connecting these data, and the things you don't know are in between the data that you know, and you try to use that connection to actually figure out what happens for the things you don't know. Now, this is one task, okay? Modeling from data. But there is another very important task, which is a task of actually classifying data. So you want now to know not the function, where they go for dinner or where they go to buy things, but you want to separate classes of data. So you want to know, if I see this particular kind of points, these dark points, and these light points, that you can find something that says, oh, a separator that finds that things to the left of this line are of this particular class, and things to the right are of these other light class. So now, what the algorithms are doing is not a function that fits all this data, but it's finding this separator that basically breaks the data into two classes: the movies I like and the movies I don't like. What is a separator? Maybe I don't like terror movies. It's enough that it's a horror movie and that's it. Or I don't like a particular actor. So you are going to say, all the movies with this actor, I don't like. All the movies without this actor, I like. So it's trying to find a separator for two classes. Okay, so very important to understand that now you are not fitting a function, but you are separating the function, the data with some kind of like separator. Okay, so this is very important. Now I'm going to challenge you with machine. So this is like, it's hard to find this line. Okay, it's hard to find this line. So I'm going to try to illustrate why it's hard to find this line with a very simple, well, in this example here, did not seem to be very hard to find the line because the line H1 is not good. The line H2 is kind of separates, but it's too close to this. So if by any chance we did not see enough data, then H2 might not be that good. But H3 is really good because it's kind of separates in the middle, the two classes. So, but there are problems that are not very easy to separate, like this one. And let's look at this example. So think about the pink dots and the blue dots. And this is like a very simple kind of like what we called one-dimensional. It's on a line. It's very simple, not a very complicated problem. It gets complicated in a second. Just hold with me for a second. But if you want to separate these, there's a problem because with one line only, because that's like how you can use that line to separate. If you put the line here, you separate these pink dots well from the rest, but not very well because the left-hand side is still a mixture of two classes. If you put it here, you also doesn't help. So I can ask you in the audience, if you think of a way to separate the pink and the blue dots in this image with just one line. It cannot be a curve. It has to be a straight line. Can you think of a way of separating these two classes with a straight line? And if you can't, I'll be able to I'll tell you how. And this is a magic thing to know. What we do is that we square the data. We move the data, we make a transformation on the data, and then guess what? There is a line that separates the two classes in a precise way. So what I'm telling you is like this. This is magic, which is this kind of like, you have your data, And now mathematically, you tweak the data, you change the form of the data, and suddenly you can find that single line that separated two classes. Okay, so if you don't remember anything else from this lecture or from this conversation, at least you can remember this picture, which is really something you can tell to anyone around you and explain what is all this machine learning about. This machine learning, or in AI, is all about finding these lines that separate data. But unfortunately, to find a line that separates data, you have to find many transformations of the data. And basically, I don't think about this, but look at the image on the left. The image on the left is the same problem as the pink and blue dots, but now in a bigger space. You cannot find one line that separates the blue from these, from the blue diamonds, from the black crosses. You cannot. If you put it here, you don't separate. If you put it there, you don't separate. But there are methods called neural nets, neural networks, that are able to find the linear separators between these data. In fact, the non-linear separators between these data. So now we are going to jump into something really much more complex. You don't need to understand anything else. The only thing you need to understand is this magic transformation, that you transform the data and you can separate. And now all the rest is harder to understand, that simple, which I try to explain in the simplest possible way. But then when you talk about deep learning, what happens is that deep learning is these very, very, very complex neural networks. And what they do, so let me just go back here. What these neural nets do is basically they apply very complicated transformations to the data. So the data is given here at the beginning. It doesn't matter, like the points or the image is given to this computer kind of architecture. And then basically there are transformations and transformations and transformations, not just squaring, but all sorts of like manipulations of the data, multiply the data by these, stretch the data there, add things to the data, all mathematical transformations, threshold the data, blah, 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 blah. A lot of transformation to the data that magically, at the end, the classes, not like movies, not like movies, but for example, objects, like this is a person, this is a motorcycle, this is a chair, all these classes, it's not the example of the movies, but now it's many classes, can actually be separated by this neural net. So what you have to understand is that what computers, a lot of these learning computers do is to basically find those transformations for the data such that they can separate the classes. And these about 10 years ago was shown to be very successful if the data are images, actual pictures, and which we call images. You actually have these pictures and you are able to find these classes of objects in the picture using these machine learning techniques. Okay, so one topic at the beginning, like the beginnings of AI, the explanation about chess and the problems of like trying to actually define AI as science and engineering. Then I jumped to tell you about machine learning, just deep learning classification. And now we are going to just finish with the third topic. And let me just, so just now switch off, and we are going to go into this robot world. And we are going to understand what these robots are all about. And they also learn, and they include all this learning, but now it's a different, like small little topic. Of course, you know, you have to understand something. I've been working on AI for more than 30 years. So I just made this exercise to select a few things to tell you today. Given that there are many more things I could have told you, but I thought that, you know, these three topics, and now we are going to delve into the robots, okay? So let's understand what is a robot. So a robot is some kind of artificial creature. So It's not built of DNA. It's not a robot. Robots are machines, are metal. There are materials, but they are artificial. They are just things. And I've worked with many, many, many robots in my life. This is just a picture I put together. Small robots. This is a golf ball playing soccer. I mean, I'm not going to focus on that. These little eyebows, these were Sony robots that we programmed, again, to play as a team, a lot of work as a team. These are cobots that I'll talk about, these large robots, and these are little humanoids, and Baxter, and all sorts of like, how can I say, all sorts of like artificial machines. But what do they do? So they basically have, this is very important to understand, they are machines that, let's focus on these cobots, that have some way of acquiring data from the environment, which we call sensors. And I'll illustrate in a second. This is very important to understand, that they have to get data. And the way to get data is to microphones or through actual sensors. Here are cameras. They have a computer that actually is able to think, and they have actuators that is able to move. Here is the robot moving at CMU, and it's moving. What matters here for you to understand is that it is moving data, reasoning, and actuation all by itself. There is no one like a drone controlling it, or it's completely by itself. And we don't see many of these robots around. In fact, you go through airports, you go through buildings, even now the autonomous cars, you might see some in the roads, but inside of our buildings, we see the Roombas. In fact, I once visited these vacuum cleaner robots, and I once visited an auditorium, I believe at Lopiano in Italy, and there was this, or maybe it was Castel Gandolfo, I don't know. It was a very large auditorium, and I could see how do we clean under these chairs? I mean, which is complicated because it's this gigantic auditorium, like any auditorium. And I could not, I could only think about, these robots, these Roombas, I mean, these kind of like vacuum cleaners, cleaning the whole thing, large, easily, because they are short and they could go under. These robots also can provide services. So robots are good to do this, but we don't see many besides the actual cleaning robots. But then I want to mention one thing here. Okay, so this problem of AI, and think about this, is not also something easy that we can just do. In fact, just to have this particular kind of robot moving around inside of Carnegie Mellon, inside of buildings, it was the focus of many, in particular 6 or 7, someone is missing here, many PhD theses, which means that, for example, Stephanie Rosenthal, one of my first students on this project, she only worked on this problem of like, how do humans ask things to the robot? How does the robot interact with the humans? And there are all these aspects. How does Brian was all interested on multiple of them collaborating. I cannot talk about all these PhD theses, but if you go to my website, you can browse and understand that this is not something that you just go to the store and buy. It's research. It's like it's ongoing developments, and we have all different sorts of like research, and these PhD students make contributions along this difficult problem of putting this together. So I just want to tell you one thing about sensors, because we come from data. I showed you the data in the machine learning world. Now I'll show you how the data is grabbed in the physical world. So there are sensors, and sensors are not we have eyes, we have ears, we have a touch, we have taste, which robots don't do, and we have a fifth one, smell. Robots also don't. But the vision is very important. And so the robots have what's called, this little thing here, this white thing is called a laser range finder. And this camera is called the Connect. And I'll just show you, so because again, let's check mark that a few things that you did not know before, maybe you know now. And so let me show you what is a laser rangefinder. A laser rangefinder, which is here in the robot, is a very interesting sensor. What it does is it only basically detects the distance to obstacles to obstacles. It reflects from obstacles at a particular height, just one plane. It's 300 and, you know, this one here, it was like, I don't know, 270 degrees. And all these lines are emitted by this sensor. And it's so beautiful that it's like a bat. You send something and you get back an echo from the objects. And so the computer can figure out how far these objects are by looking at the values that are returned by this laser. Okay, so this is when you, if you see these autonomous cars, these vehicles that the Tesla has and all these other cars are building, Argo, Aurora, it doesn't matter, Waymo, Cruise, all these companies, they have on top, most of the time, some kind of device that you look at it, and what that device is basically a laser that is much bigger than this, does the whole space, and goes around and gets where the obstacles are from everywhere. So to keep you on the lane and eventually to see these particular kind of places where the robot can be. Why are these object detection, these walls and these kind of like people in front so important to detect? It's because if this robot is moving, the first thing that it needs to do is not hit anyone, not hit the walls. So it needs to know that it can go straight and not bump into a wall. So that's why we care so much about detecting with these sensors the data about where the obstacles are. And here is an example of, see, here is like the door open and it sees like this, but don't forget it. Now, the depth camera, this Connect, is a different sensor. It's up there in the robot. And this is a very beautiful sensor because it basically, instead of getting you like just one scan down there, where are the obstacles, it sees everything in the 3D space. It's a huge camera. It's a camera that gets you, instead of just a picture, it gives you the distance to obstacles in a very large space. It's really a major accomplishment to have this type of sensor. It's 2010 only, or 2011. It's very recent, these cameras that you can actually use to find obstacles. So it can, again, it emits kind of like it's able to get information also from an image. It's an image in 3D. Instead of just one plane, gets like from everywhere where the obstacles are. So that enabled with that to have robots move, and here is a cobot moving reliably in any space. Look how beautiful they align to the center. Oh, they don't hit any obstacles, no matter what the environment is about. These are two different environments. This is in New York. This is at Carnegie Mellon. So the one on the left is Carnegie Mellon University. The one on the right is in New York at NYU. I was on sabbatical there. And basically, look, very interesting kind of like detects the environment, all different stops at the right positions and so forth. And it keeps going, and it's still going here at Carnegie Mellon. I am today in Pittsburgh, actually, for the CMU commencement, and I am here. So now one final thought with respect to these robots, which is how I'll finish in a second. So, however, so even if they move so beautifully, because it's in fact very reliable, very robust, you know, no matter what environment, it can perform tasks and it can go everywhere. And like those PhD theses I mentioned to you about, these AI, from a physical point of view, from a robot point of view, has a lot of limitations. And think about the fact that it cannot go upstairs easily. We even like the few legged robots we have, like humanoids, It's still hard. I mean, there are some dog robots that can go up, but it's still hard. They're very expensive and it's very hard. So, and they cannot open doors for sure, and it's very hard. So we realized that this is actually a difficult problem, and we introduced this concept of autonomy, symbiotic autonomy, in which robots ask for help from the humans around for the things they cannot do. It's a very interesting and beautiful concept that the robots move around, but they can ask for help. And here is an example of the robot at Carnegie Mellon, how it takes the elevator. It basically cannot push these kind of like buttons, and it says, can you please press the elevator button for me and tell me which elevator is going up. This is Stephanie actually just showing this video. And she says, oh, it's the one on the right. And then the robot goes in by itself, but it needed help to actually push the elevator button. And now inside, it also tells the human, could you please press 8 and tell me when we get to that floor? And eventually the human says, you are on 8, and it goes on to its task of moving around. So it's a very deep concept, this thing about asking for help. It also asks for help from remote humans. So if I'm in my office, I can get an email from cobots saying, I've been waiting for more than 5 minutes to some kind of like need I need to guide someone to some room, and they didn't come yet. So what should I do? And then people go and help the robot. So the robot is performing tasks, but are things that it needs help with. So it sends us email if it needs help. One final thought for this ask for help. Because of these inevitable AI limitations, if they have physical limitations that we just talked about, cannot press elevator button, but they also have many cognitive limitations. They don't know if someone says, please bring a coffee to the lab, and this is Thomas Kohler that did this work, please bring a coffee to the lab, it might not understand these words, and it might ask, I don't know, where's coffee? I don't know what's the lab. And then the humans might now not press the elevator button, but actually providing knowledge, and the robot can learn from experience the cognitive aspects. I just want to tell you that these cobot robots at Carnegie Mellon, basically by interacting with people, have learned more than thousands of facts about the environment by asking, so what do you mean by these? What do you mean by that? Manuela's office, where is Manuela's office? And they all learn these things, the coffee in the kitchen, like staplers in the office, conference rooms here. They learn the whole environment because every time you say something to the robot they don't understand, they ask, what do you mean? So in conclusion, I'm just going to have a few additional thoughts. So I told you about the beginning, which was like the AI, Alan Turing, all sorts of like Turing tests, the need for having computers that do it all, perception, cognition, and action. Then I actually just mentioned computer chess as an example. Then I jumped to just telling you a little bit about machine learning. It was like kind of a parenthesis in this kind of like AI. And then I told you about these robots, and I only focus on the sensory part and the accomplishment of them moving, and in fact this symbiotic autonomy. So, you know, it's well organized in terms of like the things you need to know or that you could have known from this conversation. But I want to just say one more thing. Don't forget that AI is code. Code means computer code, programming code. It's code. I mean, it's not that AI is something that's born. No, you have to write actually software. You have to write code. And that software runs on hardware, runs on computers. You have to have computers. So that's why people talk about the cloud, because in the cloud, there is the software, there is hardware, there are all these computers that we can run. So don't forget AI is code. Also, don't forget that machine learning, ML, as we say, is a major part of this AI story, and it uses data. So it's interesting for you to understand that when you are in your environments, and if you would like to have computers do something for you, or help assist you with tasks, that you have to gather data in a digital form. It doesn't help to gather data in paper, but if you actually make them computer digital data, then you may be able to use machine learning and AI to assist you on the tasks. One more thought. When AI solves a problem, it does not seem that's AI anymore. For example, we always use Waze, right? Waze tells you where to go. That's a beautiful AI system to route, to take into account traffic, to get all the maps in the same form. But now that it's there, you just think, oh, that's it. You know, you just use Waze. But we don't call it AI anymore. AI always seems to be the things we cannot do yet. But that's AI. There's a lot of AI around us. And so that's what AI produces, all these different kind of components. Now, AI is hard from a language point of view. Just think about the two sentences. I saw the Grand Canyon flying to New York, and I saw the Concorde flying to New York. It's exactly the same two sentences, the same sentences. I saw the whatever flying to New York. I saw the whatever flying to New York. One is the Grand Canyon, which is that mountain, that gigantic nature thing that you saw when you were flying from New York or to New York. And the Concorde is another airplane that you probably saw just passing by when you're flying to New York or something else. Look how much we know about things that enable us to understand perfectly well the difference between these two sentences, but how hard it must be for AI to distinguish the two. Another example is like this. Look at this example. Language is a very difficult problem for AI. When I dropped the ball on the table, it bounced because it was made of rubber. Now, we all understand that it refers definitely in the first sentence to the ball. There, it bounced and it was made of rubber. But the same thing, look, we just changed the verbs. When I dropped the ball on the table, it broke because it was made of glass. And now the it is probably the table. So look at this, the computer is all confused by what's this it thing? I mean, should it refer to the ball? Should it refer to the table? And then and we humans understand. So it's hard that's why AI is hard also for language. Look how difficult the last example, planning a trip. It's Wednesday. And it's Wednesday before Thanksgiving. Very different. Thanksgiving is a holiday in the United States on Thursday, in November, which is very busy in terms of traveling. Everybody goes to visit their families on Thanksgiving. Look, if you want to plan a trip on Wednesday, on a regular Wednesday, versus it's Wednesday before Thanksgiving, how will the computer know that Thanksgiving is so influences so much traveling? I mean, look how much Thanksgiving, families, traveling, getting together. My God, so many inferences that you have to do from this word Thanksgiving that for a human, it's very easy to understand that planning a trip on Wednesday before Thanksgiving is very different than planning a trip on any Wednesday. And so there is data, there is uncertainty, there is time. And so what I want to conclude, and I'll take questions, is on the actual wealth of these opportunities and issues for these human and AI. So I just want to, I know this topic here of this discussion is all about what's going beyond humans, is transhumans or whatever you are, I don't know much about the topic, but I just want to tell you that humans and AI is an opportunity for improving and assisting humans with the things they do. And I didn't have time to cover many other examples, but it's also an opportunity to understand that this is going to still be a collaboration, an integration. Humans will do things probably for many, many, many years to come better than computers. Computers will do things much better than humans, like playing chess or multiplying numbers or doing many things, looking at enormous amounts of data, or doing ways that using traffic and whatever. So there will always be human AI that can help us with our tasks, but there is this this kind of like interaction. Okay, I'll stop here. I'll be happy to answer questions now.
Well, thank you. Bene, c'è qualche intervento? Intanto grazie, ringraziamo la professoressa per questi spunti, anche alcuni anche divertenti, no? Ci hanno fatto riflettere su alcuni passaggi importanti anche di comportamento dei computer. Allora abbiamo un intervento, vediamo, sulla chat.
We have a chat question. Considering the fact that many companies nowadays are more concerned with the environment, how does AI contribute to CSR?
CSR stands for?
Exactly. What does CSR stand for?
Climate. I don't know what is CSR. I'm sorry.
No. Corporate social responsibility.
Oh, I see. Okay, I see. Very good. So yeah, so that's a completely other talk, but I can tell you one thing. The point is like this. So more and more, like I told you, companies and corporations look at using data, at collecting and eventually extracting information from data. Corporate responsibility is something I did not touch. I thought you were going to ask a question about what I said, but what I did not say much about corporate responsibility. But again, the point here is that you can have AI help with the understanding of data and guide the understanding or the actions that you want to take towards, in fact, being able to embrace these values better. However, I have to tell you one thing that it's important for us to understand, like the same way that I mentioned that cobot learned from this interaction. AI will never do the right thing up front. So what happens is that you need to have AI improve over time. And we as humans have to be generous and give guidance and correct and give feedback. And eventually these computers are able, give more data, are able to adjust as time goes because they know nothing. These machines, this AI is just what? Nothing. It's just a computer coding running. It's nothing. They don't have emotions. They don't have intuition. They don't have anything. They are running code. So we just have to make sure that for responsibility and all aspects, that you are in this business of writing some code that captures it and then correcting it over time. So there is no interest on actually just, how do you say, assume things are done correctly. Just we have to be continuously improving over time these computer programs. Sorry if the answer is general, but you have to understand that even like the work I do now at JP Morgan Chase in this firm, that's a very financial services firm, includes having algorithms that improve, learn over time to eventually be capturing the values that there are in society, the fairness, the trust, the explainability, all of that over time. But we have to write such learning algorithms over time, not just from enormous amounts of data and be done. So you use the data, you learn something, you have a computer program that does something, and then you have to have that computer program improve. When it does something wrong, we have to say, give feedback and keep improving over time. Okay.
Manuela, I'm looking at the time. We can keep asking you questions. I see there are 14 people at this stage want to ask questions. So
that's fine. I sent a message. I can stay about like 10 more minutes. So let's do that.
Okay. Considering the fact that many, second question.
I get it. You know, if the AI is going to be dangerous for people. Okay, so, right? So this is the question, right? So one thing is like this. AI, and here is like, you have to understand something. AI was invented by humans. So no matter what, it's a gift of God. It did not fall from the sky and it did not show up like that. You have to understand that humans were able to invent this. Now, given that, humans have invented many things, and all technologies, if you go to the history of science, have good and bad uses. Madame Curie, when she was developing and discovering the radio, this new element, well, led into X-rays, which saves millions of lives, and led it to nuclear weapons. So what I'm trying to tell you is like this. There is not a single example of a technological discovery, AI included, which is basically a discovery of how to use computers to process information, to help with reasoning. There is not a single example in which there are not bad and good uses of AI, okay, of technology, of discoveries. But I tell you, I really want you all, I mean, I don't know what you work on, I mean, but you have to understand one thing. Herb Simon once was in this conversation, and he said something that I'll never forget, and I keep repeating it. So he when asked the same question, is it going to be dangerous? It's going to be like a problem. Is it going to be like this? And he actually answered in a way that we know how to do. He said, we cannot look at the future thinking we are spectators of the future. We are actually actors of the future. So what means is that somehow this AI or this technology becomes what we want it to become. And it's our role in education, in loving our neighbor, in being part of society, to make sure that this technology, be it like AI, be it like whatever other technologies are developed, are not used for bad use. So otherwise, in fact, any technology, look at nuclear weapons, isn't that dangerous for humans? I'm sure it is, right? So, you know, so you have to understand that this is, so one final thing, this AI is a call to humanity. It's a call to us. We are having more and more power. It's not just the nuclear weapons. We now have computers that can do so much, and anyone in the world can use a computer. So it's now a call to us, humans. Can you handle this or not? Can you actually do this for the good of humanity or not? It's a call to us. And it's not something that's outside of us. Every single person, I always remember one thing. I mean, I know several of you are not from the focal area movement. It doesn't matter. But what matters is the following. So Chiara Lubich once said something, or at least I learned when I was very young from being in the movement, that, you know, any little thing we do makes a difference. And we cannot change the whole thing. We cannot influence but if we do well at every moment in the present, the best we can, that probably has an impact in the world. So I think that that's the way we should think about this. I cannot do more, but I can do my robots being nice. I can do my data being well processed. I can do, if you do these little things where we can influence well, probably AI will not be dangerous for humankind. Do you understand? So that is such a big goal that it's outside of your control. So let's try to do well in the things that are under our control, which is what we do at every moment, every day. So, yeah. Okay, one more. Basically, if I think if the AI can become, run away from our control and become autonomous. So it's a good question. It's a good question in the sense that even I showed you these robots that move around by themselves. The moment they will move around by themselves, and I didn't have time to explain all of this, you actually don't know where they go. You don't know. I mean, they could select, our code can select random points and send them somewhere. So it's true that they become autonomous. And in fact, it's a very interesting point about what you ask. Will we be able to control completely? Probably not. Probably not. And I tell you one more thing, you know what? We already don't control many things. we don't control many things, even before AI becomes whatever. We don't control many things. We don't even control how much our freezer freezes. We put things inside of the freezer and they get frozen. We press on gas and the car moves. So, you know, there are many things that are done, even our thermostats in the house, we don't control anymore. We set the temperature and it goes. AI one day, hopefully, will be, I mean, we don't control what Waze gives us as a route, and we do blindly what it tells us. Go left, go right, go forward, turn on the second on the left, and we are not controlling it. We can turn it off. It's a good question. I don't know how far we go. The hope is that we develop AI in parallel with developing responsible humans, and hopefully one day humans and AI can interact like we interact now between humans and humans. So,
for young people trying to get into the field, Manuela, what would you recommend they study? Or that's
very good question also, Paul. Very good question.
Just to get to me, if they wanted, for example, become one of your students, what would you look for as a background?
Very good. So this is a very good question. And so let me tell you something. If you want to be an AI researcher, an AI developer, you need to know how to program. You need to know computer science. I mean, you cannot do this AI only talking. I mean, you have to know computer science. You have to know how to use computers. And you have to know somehow, unfortunately or fortunately for many, you have to know your math. And the reason why you have to know your math is because somehow, even for that processing of data, understanding how to run in the world, it's all about mathematical functions on these data. It's math, programming. But then there is, so one thing is like this, exactly because of the questions that I've been getting, there is a big component of AI in corporations, of use of AI in corporations, in the government, that have to do with ethical problems, that have to do with how AI and humans interact, independently from the actual programming. And so AI teams are now very multidisciplinary, interdisciplinary. So if you're interested on AI, you could learn a lot of ethics and interact with psychology, and you can interact with these people who code, or sociology, you know, policies. All of these, surprisingly, is a science that is very multidisciplinary. The only thing that matters for all these people, whether they are lawyers, whether they are social scientists, whether they are psychologists, ethicals, is to understand that they are thinking about machines doing things, computers doing things. So they are the people that actually do the programming of these computers and understand how to make tasks happen. But then there are all these other people that can work in AI by understanding, how do we deploy these? How do we bring robots to an airport? What does that mean? How do people are going to interact with them? What should they look like? The whole paradigm of like making these robots, or bots, chatbots, or anything be part of the human use. That's not the programming task, but that's a lot of like understanding of automation tasks within the world. So what I'm telling you, Paul, is like this. You can, if people are interested in AI, they can become core AI developers and be computer science, electrical engineers, mathematicians, programmers, whatever. Or they can be people that are interested on AI being deployed in society or in a corporation. And then you can be a lawyer, you can be a social scientist. You have to learn about what AI is. But there are many roles for these people to be involved on deploying machines that are intelligent to perform tasks in the world.
Thank you. I'm sure our students appreciate it.
Yeah. One final thing I want to tell to this group, because I know that's more humanities group than probably the audiences I usually talk to that are more technical. I tell you one thing, I mean, I'm just making my own inferences. I tell you one thing, no matter what, think about something. AI is not going to go away. is not going to disappear. Computers are not going to disappear. It's just a fact. You cannot just grab on all computers of the world and put them in the trash. It just can't work. So let's look. It's a fact that we invented computing, that we have computers, that we can do all sorts of data together. It's a fact. And so what I think is that we cannot deny that fact. And what we have to get involved with is using these computers for good, or trying to use it for things that are interesting. So, and nobody can close their eyes and say computers are gone. It's just not possible. And so you are in a company, you have to know, what can computers help in my company? You are in education, what can computers help in education? You just cannot ignore that these things, computers and AI and data, are around. So it's like a fact of life that we need, and the more people that work on these, we need to work on these well, and to understand, you know, I don't know if you know, but, you know, again, like the focal area movement was one of the very first people, or group, very first, that used, you know, the technology of communication. I mean, how many like videos did we see in the early 70s when there were no videos? We would do I mean, the focal area movement was well ahead of any kind of group, because it was an international group. We had so many like conferences, videos. I mean, it's just crazy how much there was a use of the technology in those days. Now the technology is it's different. Technology is about AI, it's about data. How much use are we making of all this data? And so that's the only thing I'm saying, is that it's a beautiful opportunity, while in fact we have to do it well, but we cannot go back. Don't forget, it won't go back. It's always going forward.
Yes.
Thank you very much.
So thank you, Manuela, Dr. Veloso, for a fascinating talk. I'm hoping we can have you back in the future for some other events. I'm sure you've just, we have more questions and answers after today. You've started something that's fast, given a vision that I think needs to be given, and hopefully stimulates a lot of young people to also take an interest in the field and maybe even become one of your collaborators in the future.
Yeah, definitely. I mean, I look forward to it. One final thing that you should know, I actually met Piero Pasolini in person. And I really liked him. And in fact, he wrote, I mean, I exchanged some letters with him on his one of his books that I really like to read. So this was very dear to me to understand, I mean, to hear from Paul on this Cattedra Piero Pasolini. I always had a big love for Piero Pasolini, and I was very sorry when he passed away.
In fact, there's a biography of him out. We must get a copy of it to you.
Okay, yes. Thank you. I would love to see that. Paul, yes, send it to me. I'll send. Sure. This is like I'm going to keep you on that promise.
Yeah. Okay. No, I'll keep you to it. So look, thank you so much, and really appreciate all that you've done. Just to let you know, there's probably a good 70 people here today. About very 20 of us here in live, and about another 56, 57 have been connected. So
very nice. Nice meeting you all, and
I'm sure it's the beginning of something new.
Yes. You can send me email if you need. Thank you. Bye-bye. Bye-bye,
Thank
Paul.
you so much.
Bye-bye all.
Bye.
Thank you. Bye-bye. Bye-bye all.
Grazie.